Now let's have a look inside the DC motor, and then we will see whether we can use it in the form of the standard kind of block diagram system that we just represented or not. So over here you can see that DC motor is shown in this form. So we have the torque disturbance affecting the system. It has some control voltage U as the input, and it gives us the speed of the motor as the output. However, if we look at the internal structure of the DC motor, it is composed of two main parts or subsystems: an electrical subsystem and a mechanical subsystem. And you can see the internal kind of block diagram system that we have for the DC motor over here. So basically this is what we have as the control voltage, and here we have the motor speed as the output. There's also an internal feedback loop for the DC motor. Okay, so this is what we have inside the DC motor. It has nothing to do with the control system, with the feedback that we have for the control system at all. Inside the DC motor, we have the electrical subsystem, which is represented by a transfer function K over R plus S times L. And there is also the mechanical subsystem, 1 over B plus S times J, as the transfer function. And then the torque disturbance that we just discussed about, and it is happening over here, given as dH, is in the form of a signal which is being added to the output of the electrical subsystem. Okay, so it is somewhere inside there, affecting the behavior of the DC motor somewhere inside it. And obviously we can see that currently it is not in this form. So we don't have the DC motor system having the disturbance in the form of some additive term at its output. And then since we want to use this DC motor as a plant, as a process for our examples, we need to have it in this form. And now we will see whether we can do it or not, whether we can transform the block diagram representation of the DC motor into what we have here. Well, so this is our objective. We want to move the disturbance term to make it act directly on the output signal, as I just explained here, through a block HPLS. So we might also have some block over here. Let's see how we can do it. We can try to move the mechanical subsystems block in this way, so we can move it before this summing point, and obviously it will appear on the path of the disturbance if it moves there. But we have here K over R plus SL will be multiplied by 1 over B plus Sj. The summing point will remain here, and then it will also appear on the path of the disturbance, dH 1 over B plus Sj, and this gives us the output of the DC motor. And this we have it here. K is also here with a negative sign, plus U and C. Okay, so this is what we get by moving the mechanical subsystems block towards the left side. But again, if you compare it with what we are looking for, you can see that it is not actually in the same format. we don't have the disturbance being added directly to the output of the whole system. So moving the mechanical subsystem before the summing point is not enough, let's say. However, we can work with this system now in order to transform it into what we want to have in terms of the effect of the disturbance by considering each of the inputs separately. We have two inputs over here, you can see, U and DH, and then if we indeed consider the effect of one input on the output, we can find the transfer function from that input to the output separately, and afterwards we will have in the two transfer functions or two blocks which are showing the effect of the control voltage, control input, and the torque disturbance on the system. So basically we are going to apply the superposition principle, which means that we take the effect of each input individually on the output and then find the transfer function for that. So if we do so, we are supposed to end up with something like this that I'm going to draw. So we will have U with some transfer function and DH with some other transfer function, and they will give us the actual output. And once we have this, it will be in the desired format that we are looking for. How we can find the transfer functions here? We can maybe call this GP. In order to find GP, which will be indeed C over U, we should set DH to 0. So we just consider U as the input and set all the other input signals to 0. If we do so, we will have this situation. So U is here. We have K in the feedback loop, internal feedback. So K over R plus SL, B plus SJ. The summing point, and basically 0, yeah? As the input DH becomes equal to 0, the output of 1 over B plus SJ clock becomes equal to 0, and as a result we will have this. And obviously we can here neglect the summing point. So what we have is a simple feedback loop. Now we can replace it with the corresponding block, which will be so see here we will have K over R plus SL times B plus SJ plus K squared. So keep in mind that we have the negative sign here. Indeed, if you want to obtain this, you need to do like this: K over R plus SL B plus SJ over 1 plus the transfer function that we had there, R plus SL B plus SJ, times the transfer function in the feedback path, which is K. If you simplify it, you will end up with the same transfer function that we have here. Alright, then we also want to consider or to obtain the transfer function from disturbance to the output. To do that, we just set U as 0, and therefore the block diagram system that we have will be in this form. If I refer to what we have here, So we will have, let me first maybe draw it here. We will have 0, K, K over R plus SL, B plus Sj, one over B plus Sj, and we have dH, the main input here, and this gives us the output C. And now since dH is our main input, I can kind of redraw this in this form. So dH is here. We have 1 over B plus Sj with plus signs plus, this gives us C, which is the actual output, and then from C we have K. Since the U input is equal to 0, we can just replace K with minus K, or I can consider some minus 1 here, which shows us the negative sign that we had here. And then we have K over R plus SL, B plus Sj, which is giving us the signal to be added at this summing point. Now, in order to simplify this, we can see that over here we have a feedback configuration, which is a positive feedback, referring to the sign here, with minus K squared over R plus SL times B plus Sj, and the feedback pass, and 1 at the feed forward indeed pass. So therefore we can redraw it in this form: 1 over B plus Sj, and then we will replace the whole thing here with a single block. I will indeed replace all these with minus K squared. So in order to obtain the transfer function for this feedback configuration, we will have the transfer function in the forward pass over 1 minus 1, which is the transfer function in the forward pass, times the transfer function in the feedback pass, which is indeed equal to minus K squared over R plus SL, B plus Sj. And again, if we simplify this, we will get the transfer function that I'm going to write down over here. So indeed we will have R plus SL times B plus Sj plus K squared, and at the numerator we will have R plus SL times B plus Sj. And then these B plus Sj's will cancel each other, and as the final transfer function we will have R plus SL at the numerator and R plus SL times B plus Sj plus K squared at the denominator. And afterwards we can say that now for the DC motor system we will have the whole system in this form. we have the same transfer function that we obtained here, r plus sl, r plus sl, b plus sj plus k squared for the disturbance, dh, and for the process we have k over the same denominator, r plus sl, b plus sj plus k squared. Okay, and now we can see that it is in the form that we were looking for. So if you compare it with what I already have drawn here, you can see that it is indeed fitting that standard form that we are looking for. Okay, so therefore this will be the form in which we are interested, and we obtain this by considering the superposition principle.